This is our workshop paper presentation on learning manifolds for sequential motion planning. In task and motion planning, a task can often be broken down into a sequence of subtasks where each subtask has one or more constraints associated with it. One way of describing constraints in planning is with implicitly defined manifolds in configuration space. For example, a mobile robot may have to stay within a certain range of a communications tower, or the end effector of an arm may need to maintain contact with an object. These manifolds M can be described as inequality or equality constraints defined by their implicit function hm. Some constraints may be easy to describe analytically, but some not. In this work, we focus on data-driven approaches to learning manifold constraint representations for complex planning tasks. We explore two methods for learning implicit constraint manifolds: equality constraint manifold neural networks, or ECOMAN, which is a novel method for learning representations of implicit functions, and variational autoencoders, which learn a distribution that can be sampled to produce new constraint-adhering configurations for planning. ECOMAN is a neural architecture for learning equality constraints which takes a configuration Q as input and outputs the prediction of the implicit function hm of Q. For equality constraints, hm of Q should be 0 for all configurations on the manifold. ECOMAN works by using local PCA to align the row space of the data covariance matrix with the null space of the network Jacobian, and the null space of the data covariance matrix with the row space of the network Jacobian. ECOMAN is trained to minimize the projection errors of these spaces to each other. The second method we investigate, the variational autoencoder, is a method for learning a generative model of a set of data. They consist of an encoder, which embeds data points as a learned Gaussian distribution, and a decoder, which takes a sampled latent vector and produces a reconstructed point in the original space. We evaluate these two methods on 6 datasets with configuration spaces ranging from 2 to 8 degrees of freedom. 2 of these are inequality constraints, and thus we only test the VAE on them, and the other 4 are equality constraints. First, we compare the performance of the two model architectures using the implicit function value hm on the datasets used when training the models. In the case of the VAE models, we take the reprojected data and evaluate each configuration with hm. In the case of ECOMAN, the output of the network is the estimated implicit function value of the input, so we directly use it. We report the mean and standard deviation hm of Q of each task dataset. Second, we evaluate the implicit function hm on newly generated points from the VAE's learned embedding space. We generate 100,000 new data points using the trained decoder for each constraint model. These generated points are near but not exactly on the manifolds. Third, we incorporate a learned manifold into a sequential planning framework introduced in previous work called Sequential Manifold Planning, or SMP. The task is for a point to move from one paraboloid to another where the paraboloids are connected by a sphere. We use ECOMAN to learn the sphere constraint and SMP to generate a path across all 3 manifold constraints. In this work, we demonstrate how to learn equality and inequality constraint manifolds with 2 different methods, which can be incorporated into an existing planning framework. In the future, we'd like to address some limitations, including testing on higher dimensional manifolds and more complex problems, learning manifolds from real robot datasets, and integrating the VAE into the planner. Thank you.